Hello everyone and welcome back. We finally reached the summit of our linear algebra journey, and I hope the path getting here has been both rewarding and insightful. Today, I'm excited to introduce one of the most powerful and elegant ideas in all of linear algebra, the singular value decomposition, or SVD, a decomposition that in many ways rules them all. If you've enjoyed the course so far, don't forget to subscribe and stay tuned for more updates, courses, and deep dives into mathematics and related topics. Stay tuned. Now, let's get started.
Today, we arrive at one of the most powerful ideas in linear algebra, the singular value decomposition, or SVD. I do not want to present SVD as a random formula at the end of the course. I want to present it as the answer to a question that has been following us from the beginning. How simple can a matrix really be? Every time we studied a new decomposition, we were trying to take a complicated matrix A and rewrite it as simpler pieces. But every decomposition came with a catch. Sometimes A had to be square. Sometimes A had to be invertible. Sometimes A needed enough eigenvectors. Sometimes A had to be symmetric. Sometimes the columns had to be independent. SVD is different. SVD says give me any real matrix A, square or rectangular, symmetric or not symmetric, invertible or not invertible, full rank or rank deficient, and I can still decompose it. The formula is A equals U sigma V transpose. Here U and V are orthogonal matrices, and sigma is a diagonal-like matrix containing non-negative numbers called singular values. This is why SVD feels like the grand finale of linear algebra. It takes the pieces we already understand, rotations, reflections, axis scaling, orthogonal bases, symmetric matrices, and eigenvectors, and combines them into one universal decomposition. The key is to read the formula from right to left. First, V transpose chooses a better coordinate system for the input. Then sigma scales, deletes, or embeds coordinates. Finally, U places the result into the correct output orientation. So the entire transformation is choose input directions, scale them, and place them in output directions. Before we build SVD, let us remember the decompositions we have already seen. Start with elimination. When we write A equals μU, we are breaking A into a lower triangular matrix and an upper triangular matrix. This is useful because triangular systems are easy to solve. But a clean LU factorization without row swaps depends on good pivots appearing in the right places. If a pivot is 0, we usually need row exchanges, and the better statement becomes PA equals LU. So LU is powerful, but the matrix has to cooperate with elimination. Then came QR decomposition. For a matrix A with independent columns, we can write A equals QR, where Q has orthonormal columns and R is upper triangular. This taught us that orthonormal bases are special because they preserve lengths and angles, but the clean thin version of QR depends on the columns of A being linearly independent. Then came eigendecomposition. For a square matrix A, we hope to write A equals PDP inverse, where D is diagonal. This is beautiful because diagonal matrices are easy. They simply scale coordinate axes. But eigendecomposition has strong conditions. A must be square, and A must have enough independent eigenvectors to form P. Many square matrices do not. Then came the spectral theorem for symmetric matrices. If A is real and symmetric, then we can write A equals PDP transpose. The eigenvectors can be chosen orthonormal, the eigenvalues are real, and the inverse of P is just P transpose. Geometrically, a symmetric matrix rotates into an orthonormal eigenbasis, scales along perpendicular axes, and rotates back. This is one of the cleanest stories in linear algebra, but it requires symmetry. The matrix must satisfy A equals A transpose. So here's the pattern. LU asks for good pivots unless we allow row swaps. QR asks for independent columns, at least in the clean thin form. Eigendecomposition asks for a square matrix with enough eigenvectors. Orthogonal diagonalization asks for symmetry. Every decomposition gives us simplicity, but each one demands something from A. Then SVD arrives and says, no symmetry, no squareness, no invertibility, no full rank assumption. For every real matrix A, we can write A equals U sigma V transpose. To understand SVD, we do not need a completely new language. We need to combine old ideas. First, diagonal matrices. A diagonal matrix does not mix the coordinate axes. For example, the matrix with 3 in the first diagonal entry and 1 in the second diagonal entry stretches the x direction by 3 and leaves the y direction unchanged. Diagonal matrices are simple because each axis acts independently. Second, orthogonal matrices. A matrix P is orthogonal when P transpose P equals the identity matrix. That means P inverse equals transpose. Geometrically, orthogonal matrices rotate or reflect. They preserve lengths and angles. If you apply an orthogonal matrix to a circle, it stays a circle. If you apply it to a sphere, it stays a sphere. Third, symmetric matrices. A real symmetric matrix satisfies A equals A transpose. This condition is deeper than it looks. Symmetric matrices have orthonormal eigenvectors, and in that eigenvector basis, the matrix becomes diagonal. That is the spectral theorem. If A is symmetric, then A equals PD key transpose. This means a symmetric matrix can be understood as rotate into the eigenvector basis, scale along perpendicular directions, and rotate back. SVD takes this beautiful symmetric matrix story and extends it to every real matrix. But most matrices are not symmetric. Many are not even square. So we need a way to use symmetric matrices even when A itself is not symmetric. The trick is to manufacture symmetry from A. Before we manufacture symmetry, we need to be clear about rectangular matrices. An m by n matrix A represents a linear transformation from Rn to Rm. The input vector has n entries, the output vector has m entries, so a rectangular matrix can move vectors between different spaces. A 2 by 3 matrix takes vectors from 3-dimensional space and sends them into 2-dimensional space. A 3 by 2 matrix takes vectors from 2-dimensional space and places them into 3-dimensional space. This is why ordinary eigenvectors are not enough. An eigenvector satisfies AV equals lambda V, but that equation only makes sense when AV and V live in the same space. For a rectangular matrix, V might live in R3, while AV lives in R2. They are not even the same kind of object. So for rectangular matrices, we need a new idea. Think about the matrix E, with first row 1, 0, 0, and second row 0, 1, 0. This matrix takes the vector x, y, z, and sends it to x, y. It keeps x, keeps y, and deletes z. This is a dimension eraser. Now think about the matrix B with first row 1, 0, second row 0, 1, and third row 0, 0. This matrix takes x, y, and sends it to x, y, 0. It adds a 0 coordinate. This is a dimension adder. Rectangular diagonal-like matrices can scale some coordinates and delete or add dimensions. This is why sigma in the SVD is allowed to be rectangular. If A maps Rn to Rm, then sigma also maps Rn to Rm. Sigma has the same shape as A. Now we come to the central trick. If A is any real matrix, maybe square, maybe rectangular, maybe non-symmetric, then we can form two special matrices, A transpose A and AA transpose. These two matrices are always square. If A is m by n, then A transpose A is n by n, it acts on the input space, Rn, and AA transpose is m by m, it acts on the output space, Rm. Even better, both matrices are symmetric. The transpose of A transpose A is A transpose A. The transpose of AA transpose is AA transpose. So from any matrix A, we have created two symmetric matrices. This is the bridge from the spectral theorem to SVD. Because symmetric matrices have orthonormal eigenvectors, A transpose A has an orthonormal eigenbasis in the input space, and AA transpose has an orthonormal eigenbasis in the output space. Both A transpose A and AA transpose are positive semi-definite. For A transpose A, take any vector x. Then x transpose AX equals AX transpose AX, which equals the squared length of AX. That is always greater than or equal to 0. So the eigenvalues of A transpose A are non-negative. The same idea works for AA transpose. This is why singular values are real and non-negative. Singular values are square roots of the eigenvalues of these symmetric matrices. So the plan is simple. Use A transpose A to find special input directions. Use AA transpose to find special output directions. Use the square roots of the shared non-zero eigenvalues as the stretching factors. Those stretching factors are the singular values. Let us give names to the pieces. The eigenvectors of A transpose A are called the right singular vectors of A. They live in the input space. They become the columns of V. The eigenvectors of AA transpose are called the left singular vectors of A. They live in the output space. They become the columns of U. The singular values are the non-negative numbers, sigma 1, sigma 2, and so on. They go into sigma. The most important equation is AVI equals sigma I times UI. This is the heart of SVD. It says start with a special unit vector VI in the input space. Apply A. The result points exactly in a special unit direction UI in the output space. Its length is sigma I. So a right singular vector is a special input direction. A left singular vector is the corresponding output direction. A singular value is the amount of stretching between them. If sigma I is large, A strongly amplifies that input direction. If sigma I is small, A nearly crushes that direction. If sigma I is 0, A completely destroys that direction and sends it to 0. This is how SVD reveals rank. The rank of A is the number of non-zero singular values. In geometric language, rank counts how many independent directions survive the transformation. Now we can state the theorem. For any real m by n matrix A, there are orthogonal matrices U and V and a rectangular diagonal matrix sigma, such that A equals U sigma V transpose. The columns of V are the right singular vectors. The columns of U are the left singular vectors. The diagonal entries of sigma are the singular values. The formula A equals U sigma V transpose should be read from right to left. First, V transpose acts. Because V is orthogonal, V transpose is also orthogonal. So V transpose rotates or reflects the input space. It doesn't stretch, it doesn't squash, it only changes orientation. Then sigma acts. This is where the real distortion happens. Sigma scales the coordinate axes by the singular values. Large singular values stretch, small singular values squeeze, zero singular values collapse directions completely. Sigma may also erase dimensions or embed the result into a larger space. Finally, U acts. Because U is orthogonal, it rotates or reflects the output into its final position. So every matrix can be understood as three simpler operations. First, rotate or reflect the input. Second, scale, erase, or embed coordinates. Third, rotate or reflect the output. This is the geometric movie of SVD. A circle becomes an ellipse. A sphere becomes an ellipsoid. As singular values are the lengths of the principal semi-axes, the right singular vectors are the input directions that become those axes. The left singular vectors are the output directions where those axes land. Right singular vectors tell us which input directions matter. Singular values tell us how much those directions are stretched. Left singular vectors tell us where those directions land. Now let us compute an SVD completely from start to finish. Our first example is a square, non-symmetric matrix. A equals the 2 by 2 matrix with first row 3, 3, and second row 1, -1. This matrix is square, but it is not symmetric. So we do not use the spectral theorem directly on A. Instead, we begin by computing A transpose A and AA transpose. First, A transpose equals the matrix with first row 3, 1, and second row 3, -1. Now compute A transpose A. A transpose A equals the matrix with first row 3, 1, and second row 3, -1, multiplied by the matrix with first row 3, 3, and second row 1, -1. The result is the matrix with first row 10, 8, and second row 8, 10. Now compute AA transpose. AA transpose equals the matrix with first row 3, 3, and second row 1, -1, multiplied by the matrix with first row 3, 1, and second row 3, -1. The result is the matrix with first row 18, 0, and second row 0, 2. Notice the important point. A itself was not symmetric, but both A transpose A and AA transpose are symmetric. Now we use their eigenvalues and eigenvectors to build the SVD. Start with A transpose A. A transpose A equals the matrix with first row 10, 8, and second row 8, 10. To find its eigenvalues, solve determinant of A transpose A minus lambda I equals 0. A transpose A minus lambda I equals the matrix with first row 10 minus lambda, 8, and second row 8, 10 minus lambda. The determinant is 10 minus lambda squared minus 64. Set that equal to 0. 10 minus lambda squared equals 64. So 10 minus lambda equals plus or minus 8. Therefore, the eigenvalues are lambda 1 equals 18 and lambda 2 equals 2. The singular values are the square roots of these eigenvalues. So sigma 1 equals the square root of 18, which is 3 times the square root of 2, and sigma 2 equals the square root of 2. Now find the eigenvectors of A transpose A. For lambda 1 equals 18, solve A transpose A minus 18I times V equals 0. This gives the equations negative 8x plus 8y equals 0 and 8x minus 8y equals 0. So x equals y. A corresponding eigenvector is 1, 1. Normalize it to get v1 equals 1 over the square root of 2 times the vector 1, 1. For lambda 2 equals 2, solve A transpose A minus 2i times v equals 0. This gives x plus y equals 0, so y equals negative x. A corresponding eigenvector is 1, negative 1. Normalize it to get v2 equals 1 over the square root of 2 times the vector 1, negative 1. These are the right singular vectors. They become the columns of V. So V equals the matrix whose first column is 1 over the square root of 2 times 1, and whose second column is 1 over the square root of 2 times 1, negative 1. Now look at AA transpose. AA transpose equals the diagonal matrix with entries 18 and 2. So its eigenvalues are immediately 18 and 2. The eigenvector for lambda 1 equals 18 is u1 equals the vector 1, 0. The eigenvector for lambda 2 equals 2 is u2 equals the vector 0, 1. These are the left singular vectors. They become the columns of U. So U is just the identity matrix. Now build sigma. Sigma is a 2x2 diagonal matrix with singular values on the diagonal. Therefore, sigma has 3 square root 2 in the first diagonal entry and square root 2 in the second diagonal entry. So the decomposition is A equals U sigma V transpose. In this example, U is the identity matrix. Sigma is diagonal with entries 3 square root 2 and square root 2, and V has columns 1 over square root 2 times 1, 1, and 1 over square root 2 times 1, negative 1. Let us verify the decomposition. Because U is the identity matrix, A equals sigma V transpose. V transpose equals V, in this example, because this V is symmetric. So sigma V transpose is the diagonal matrix with 3 square root 2 and square root 2 on the diagonal, multiplied by the matrix with first row 1 over square root 2, 1 over square root 2, and second row 1 over square root 2, negative 1 over square root 2. The first row becomes 3, 3, the second row becomes 1, negative 1. So, sigma V transpose equals the original matrix A. Now let us check the geometric meaning. The first right singular vector is v1 equals 1 over square root 2 times the vector 1, 1. Apply A to v1. The result is the vector 3 square root 2, 0. That is 3 square root 2 times u1. So AV1 equals sigma 1 times u1. The second right singular vector is v2 equals 1 over square root 2 times the vector 1, negative 1. Apply A to v2. The result is the vector 0, square root 2. That is square root 2 times u2. So AV2 equals sigma 2 times u2. This is exactly what SVD promised. Each special input direction VI gets sent to one clean output direction UI, scaled by sigma I. Now let us do a rectangular example. Consider A equals the 2x3 matrix with first row 1, 1, 0 and second row 0, 0, 2. This matrix maps R3 to R2. A vector xyz is sent to x plus y, 2z. So the matrix combines the x and y coordinates, stretches the z coordinate by 2, and outputs a vector in 2 dimensions. Because A is rectangular, ordinary eigenvectors of A do not make sense. But SVD still works. First, compute A transpose. A transpose is the 3x2 matrix with first row 1, 0, second row 1, 0, and third row 0, 2. Now compute A transpose A. A transpose A equals the 3x3 matrix with first row 1, 1, 0, second row 1, 1, 0, and third row 0, 0, 4. This matrix acts on the input space R3. Now compute AA transpose. AA transpose equals the 2x2 matrix with first row 2, 0, and second row 0, 4. This matrix acts on the output space R2. The input side has dimension 3, and the output side has dimension 2. But the non-zero eigenvalues of A transpose A and AA transpose will match. Now find the eigenvalues and eigenvectors of A transpose A. A transpose A equals the 3x3 matrix with first row 1, 1, 0, second row 1, 1, 0, and third row 0, 0, 4. The z direction is easy. The vector 0, 0, 1 is sent to 0, 0, 4. So it is an eigenvector with eigenvalue 4. Therefore, lambda 1 equals 4, and v1 equals the vector 0, 0, 1. Now look at the xy block. The 2 by 2 block with all entries equal to 1 sends the vector 1, 1 to 2, 2. So the eigenvalue is 2, with eigenvector 1, 1 in the xy plane. Normalize it to get v2 equals 1 over square root 2 times the vector 1, 1, 0. The vector 1, negative 1 in the xy plane is killed by that block. It is sent to 0. So lambda 3 equals 0, with eigenvector v3 equals 1 over square root 2 times the vector 1, negative 1, 0. So the eigenvalues of A transpose A are 4, 2, and 0. The singular values of their square roots. Sigma 1 equals 2, sigma 2 equals square root 2, sigma 3 equals 0. The right singular vectors are v1 equals 0, 0, 1, v2 equals 1 over square root 2 times the vector 1, 1, 0, and v3 equals 1 over square root 2 times the vector 1, negative 1, 0. These become the columns of V. Now look at AA transpose. AA transpose equals the 2 by 2 diagonal matrix with entries 2 and 4. We list the eigenvalues in descending order to match the singular values. The eigenvalue 4 has eigenvector u1 equals 0, 1. The eigenvalue 2 has eigenvector u2 equals 1, 0. So, U equals the 2 by 2 matrix with first column 0, 1 and second column 1, 0. Now build sigma. The original matrix A is 2 by 3. Therefore, sigma must also be 2 by 3. The singular values are 2, square root 2, and 0. So sigma is the 2 by 3 matrix with first row 2, 0, 0, and second row 0, square root 2, 0. Now we have all three pieces. U has columns u1 and u2. Sigma contains the singular values. V has columns v1, v2, and v3. And the decomposition is A equals u sigma v transpose. Let us verify the rectangular SVD. V transpose has first row 0, 0, 1. Its second row is 1 over square root 2, 1 over square root 2, 0. Its third row is 1 over square root 2, negative 1 over square root 2, 0. U sigma equals the matrix with first row 0, square root 2, 0, and second row 2, 0, 0. Now multiply U sigma by V transpose. The first row becomes 1, 1, 0. The second row becomes 0, 0, 2. So U sigma V transpose equals the original matrix A. Now interpret the singular vectors. The first right singular vector is v1 equals 0, 0, 1. This is the pure z direction. Apply A to v1. The result is 0, 2. That equals 2 times u1. The second right singular vector is v2 equals 1 over the square root of 2 times the vector 1, 1, 0. Apply A to v2. The result is the vector square root of 2, 0. That equals square root of 2 times u2. So AV2 equals square root of 2 u2. The third right singular vector is v3 equals 1 over the square root of 2 times the vector 1, negative 1, 0. Apply A to v3. The x and y entries cancel. The result is the 0 vector. So AV3 equals 0. This means v3 is a null space direction. The matrix takes a three-dimensional input space and sends it into a two-dimensional output space. Two directions survive, one direction is destroyed. That is why the singular values are 2, square root of 2, and 0. The rank is the number of non-zero singular values. So this matrix has rank 2. SVD also explains rank and the four fundamental subspaces. Suppose A has rank R. That means there are exactly R positive singular values, sigma 1 through sigma R. The remaining singular values are 0. The first R right singular vectors v1 through vr span the row space of A. These are the input directions that survive. The remaining right singular vectors vr plus 1 through vn span the null space of A. These are the input directions that get sent to 0. On the output side, the first R left singular vectors u1 through ur span the column space of A. These are the directions where outputs actually land. The remaining left singular vectors ur plus 1 through um span the left null space. These are output space directions that A never reaches. So SVD does not just factor a matrix, it organizes the entire geometry of A. It tells us which input directions matter, which input directions vanish, which output directions are reached, and which output directions are impossible. This is why SVD is sometimes described as the decomposition that understands all four fundamental subspaces at once. There is another interpretation of SVD that is incredibly important for applications. Instead of viewing SVD as a product of three matrices, we can view it as a sum. A equals sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose plus more terms, up to sigma R UR VR transpose. Each term UI VI transpose is a rank 1 matrix. Each rank 1 matrix is weighted by the singular value sigma I. So SVD says that a complicated matrix is a sum of simple rank 1 patterns. The first pattern is weighted by the largest singular value. The second pattern is weighted by the second largest singular value, and so on. Because the singular values are arranged in decreasing order, the early terms usually capture the strongest structure. The later terms capture smaller details, fine texture, or noise. This is the idea behind low-rank approximation. Instead of keeping all the terms, we keep only the first k. A sub k equals the sum from I equals 1 to k of sigma I UI VI transpose. This gives a rank k approximation of A. For images, this means we can treat a grayscale image as a matrix of pixel brightness values. The first few singular values often capture the broad shapes. More singular values add detail. Many real images are not exactly low rank, but they are often approximately light rank. SVD also connects directly to PCA. If a centered data matrix is decomposed using SVD, the right singular vectors give principal directions in feature space, and the singular values tell us how much variation lies in each direction. That is why SVD appears in image compression, noise reduction, dimensionality reduction, recommendation systems, and data analysis. It turns a large matrix into a hierarchy of patterns ordered by importance. Earlier decompositions gave us powerful ways to simplify matrices, but they came with conditions. Eigendecomposition asks for a square matrix with enough eigenvectors. Orthogonal diagonalization asks for symmetry. But SVD works for every real matrix. For any m by n real matrix A, we can write A equals U sigma V transpose. U and V are orthogonal matrices. Sigma is a rectangular diagonal matrix with non-negative singular values. The columns of V are right singular vectors. They live in the input space. The columns of U are left singular vectors. They live in the output space. The singular values measure stretching strength. Geometrically, V transpose rotates or reflects the input space. Sigma scales, deletes, or embeds dimensions. U rotates or reflects the output space. Algebraically, SVD comes from the symmetric matrices A transpose A and AA transpose. A transpose A equals V sigma V transpose. AA transpose equals U sigma transpose U transpose. So SVD takes the clean eigenvector story from symmetric matrices and extends it to every matrix. Finally, SVD can also be written as a sum of rank 1 patterns. Keeping only the largest singular values gives low rank approximation and compression. So what does SVD tell us? It tells us that every matrix, no matter how complicated it looks, has hidden orthonormal input directions and hidden orthonormal output directions. In those coordinates, the matrix simply stretches, crushes, deletes, or embeds. With the right coordinates, every matrix is simple. That is the singular value decomposition.
Don't forget to subscribe and hit the notification bell. And see you in the next lecture.